So quantum mechanics can solve this problem. How is it done? Alice sends encoded single photons to Bob, where the information for this key which we want to exchange is encoded onto this polarization which we mentioned already. And now the nice thing is that those quantum states, they cannot be measured or copied or manipulated without destroying this fragile quantum state, like the superposition we mentioned. If one tries to gain information on the superposition state of those two polarizations, for instance, then the state will be disturbed and errors are introduced in the transmission channel. So what Alice and Bob do is simply, Alice prepares a sequence of randomly polarized photons, sends them across to Bob. Bob does his measurements, and later they talk to each other over a normal public channel, and then they can tell if the photons if they are okay or not, if they have experienced any disturbance, or if somebody tried to measure them. And so they can tell if that transmission was secure or not. And from that data which Bob receives and Alice sends, they can extract a secure key. I will not enter the whole protocol, it's because I will consume the rest of the time. So I just wanted to convey this kind of key principle. So the key security relies on the fact that a single quantum system can never be measured without disturbing it. This is also related to the Heisenberg uncertainty, for instance, where you can never measure, you can never determine all properties of a single particle at once to arbitrary accuracy. If you try to measure one property, like position, very accurately, then for instance the momentum of a particle becomes uncertain, and vice versa. And this is actually essentially the same, the key mechanism here. Also, I'd like to point out at this point, the correlation here can also be created by entangled photons. So Alice and Bob can simply share entangled photons, measure them, and use those results which they receive, the plus and ones and so on, the plus and minus, as the input for the key. And then they will test the entanglement to see if the channel is secure. Sorry. Yeah.
Do you just use like optical fibers to connect Alice and Bob together? Like, how do you send the photon?
Yeah, that's a good point. There are two ways to do it actually. One is optical fiber, and the other one is free space. So those are the two methods today that we have. But I'll say a little bit about that in a moment. I would like to point out here, if you're interested in more details, there are some nice review papers. So the original ones are 1984, 1991, but for instance, Nicolas Gisser in 2002 or Scarani et al. In 2009, or actually it has appeared now. They're good review papers to get into this topic. So that ties into the question. Okay, if we use optical fibers for that kind of protocol, then the key problem here is we have to have a direct link. We can only have one stretch of passive fiber. And contrary to classical communications, we cannot include amplifiers. So why? Because an amplifier would just be the same as a cloning process, an attacking process. So it will introduce errors and disrupt the transmission. So the current state of art is with optical fibers in the lab, essentially around 200 kilometers. This is one sample of spools, which actually was done in Vienna, 100 kilometers of fiber. I find it amazing. That's 100 kilometers sitting in the lab. And so several experiments have shown that this can be reached. And that's already, this one for instance, 250 kilometers is the far limit. Yeah.
Do they use silicone fibers, or do they use that new fancy like?
No, this is just a pure silica fiber. the kind of the best fibers you can get at the moment, which are very optimized for long distance transmission, low loss. And so this is essentially the fundamental limit of the scattering of the material itself, the pure material. And yeah, that's right. There could be new fiber technologies emerging, which can maybe go also bring to further, but there's nothing viable on the horizon at the moment. Simply also because the main driver for optical fibers is of course telecom industry, and telecom is as far as I know, they're kind of happy with the technology at the moment, so of course I'm not explaining that. This is also an interesting slide. There's recently, actually HEC did a survey on research groups worldwide who are active in this kind of area of quantum key distribution. And the little dots are all around the place, Europe and North America and Asia. And essentially it's close to 100 groups worldwide, so in theory and implementations working in this area. This was done by Quantum Works, or in the framework of Quantum Works. So this also should show that this is not only pure concepts, but it's really moving into a real world direction. In last year there was an experiment in Vienna to do a quantum network in the city with optical fibers, and this is like the total distance of about 70 kilometers was covered with such a network and various nodes. So why did I want to mention that? So with optical fibers, this is about as far as you can get at the moment with today's technology. We can do those maybe 200 kilometers, and we can do like an intercity network. The other way of transmitting photons is in free space. There has also been quite a range of experiments in the last decade. This was so far it's the longest transmission for entangled photons, over 144 kilometers on the Canary Islands from one island to the other. And there, so the entangled photons were created on a lab on this side, and one of them was sent through a little telescope across the 144 kilometers direct out of sight and received in this optical ground station on Tenerife. And there, essentially, the incoming beam, so this is like a 1 meter telescope, and this incoming beam was focused down to about 0.5 millimeter so that it matched these the little signal photon detectors here. And simply by recording the timing on that side of those photon arrivals and comparing them to the times of the entangled particle on the other side, so one obtains such a timing distribution, for instance. So the scale here is nanoseconds, so it's all around like plus minus 1 nanosecond, but it has an offset of about 0.5 millisecond. Actually, this is alone. It should be 479 microseconds, so 0.5 millisecond, which is the line of the time of flight for the light signal across. And this is also for free space transmissions about as far as it can go. If you go travel further, the curvature of the Earth comes in, and obstacles, of course. You have I mean, this was like as good as you can have it. There's just an ocean in between, and you've got like mountains on either side which are 2,000 meters high, and that's not really a practical scenario. But